I think everyone's still here, so I'll just get started now. So previously we talked about formal verification and reachability analysis using flow pipe construction. Right, so I explained the general reachability algorithm in terms of sort of broad sets and set operations. And so this time what I'm going to cover is some very specific sets that have been considered and how to do these various set operations on them. I mentioned before that there's different classes of hybrid systems as well, right? So depending on the complexity of the continuous dynamics, you can have timed automaton, linear automaton, rectangular hybrid automaton, nonlinear hybrid automaton. So the class of systems I'm going to focus on is linear hybrid automaton. And then near the end, if there's time, I'll talk about how to use methods for sort of hybrid automata with linear ODEs on systems that have nonlinear ODEs. So for linear continuous systems, just sort of a short review. If you have a linear system of ordinary differential equation x dot equals ax, there's a solution to the system. You can write it as e to the at x naught, where t is your time. This is a little bit strange because it looks like a closed form solution, but actually computing this, it's a matrix exponential because this a is a matrix. So there's various ways to compute this. One way to define it is as this sort of infinite series as well, but it's probably less important. There's some way to compute this, which is just another matrix. And then if you take an initial state, multiply it by the matrix, you'll get the state after some amount of time has elapsed. So we don't want to deal with individual states. Instead, we want to deal with sets of states. So if you have a set, this sort of big X naught, and your initial state is within that set, then you want to find the solution for all the sort of trajectories that start in that set of states. So we can write it as something like this, that x at time t, x of t is e to the at times the set x naught. This is a little bit strange because you can multiply a matrix times a vector, right? But what does it mean to multiply a matrix times a set? So what this is actually, what we want is we want our set to support this linear transformation operation. So you have a set of states, and you should be able to compute another set of states that's basically matrix multiplication of this matrix times every point within this set. So we start with a set, we end with a set, and there's this correspondence. What about if we care about the solution at multiple steps, right? So one thing we can notice is that if we want the solution at time 2t, this is just the time elapse, again, for one time step times the set of states that we had already computed. So if you expand this out, it's a matrix multiplication times this system, which is the same thing mathematically as just taking e to the a2t times x naught, which is sort of what you'd expect, right, if you just substitute t for 2t. Since we're doing this computation sort of step by step in flow pipe construction, though, sometimes it's sort of more efficient to just multiply it by another matrix instead of starting from the initial states again. But we'll see that later. When you have a linear system with inputs, so x dot equals ax plus bv of t, you can also write the solution. It's a little bit more complicated, but it essentially consists of two parts. So you still have this a e to the at times x naught. This is sort of the input-free solution. And then you can add the sort of effects of the inputs over time. And this is a little bit more complicated, but there's ways to simplify it. This is for a single point again, if you have a single vector x naught. And u is or the v is a function that's changing over time, so it's your input function over time. When you have sets of states, again, you could imagine your initial state is within some set, but now your inputs are also within some set. So what does this mean? This means that there's some set of states. Your inputs are changing over time, but they're staying within that set of states. So you're sort of looking at all possible sort of functions that stay within that set over time. The solution, we can write it as something like this. So again, we have this sort of input-free part and the effects of the inputs. Now we no longer have a plus here, but we have something slightly different, which is this O plus notation, but this is Minkowski sum. So the Minkowski sum of two sets of states is the addition of every 2 points within the sets. And so that's a common operation that's used in reachability analysis tools. What does that look like graphically? It's something like this. So again, the Minkowski sum is defined to just be the sum of, take some element from x and some element from y, add them together, and that element is in the Minkowski sum. sort of pictorially, you could imagine this is the x I chose, this is the y I chose, and then x plus y is here. And the Minkowski sum then is this sort of outer box. So one thing it's useful for is bloating. I mentioned before, if we want to reason between sets of states, you can figure out how how far a state can evolve in a small amount of time, and then you bloat a set of states, and then you'll contain everything that happens between sets of states. But it's useful in other parts, for example, considering inputs. Another way to think of this operation is sort of if you had the square and the circle, and you sort of dragged one over the border of the other, you'd get the Minkowski sum as well. So solution simplification. So the inputs will change over time, but the sort of set of states that they're contained in is fixed. So you can imagine if you have a function that's an input that sort of over time picks a value within this set, there's an equivalent function that basically just flips time around. So everything that happened at the end will happen at time 0 and sort of vice versa. So you have this reflection property. So what that allows you to do is get rid of this, this part here too, because you can simplify this t minus s to just be s, which is what you're integrating, because for every forward function there exists a reverse function. So this is a little bit simpler. There's other things you can do. If you similarly to when you're doing continuous post operation, you compute the set of states at fixed points in time, and then you do some sort of bloating. What's typically done for inputs is that you consider fixed inputs at each step, and then you use bloating to account for what could be the difference between the fixed inputs, the solution with fixed inputs, and the solution with inputs that change over time. So I'm just going to describe the fixed input case, which is a little bit more difficult. There's some math to derive how much you need to bloat by when you don't have fixed inputs. So we're just looking at this sort of input effects term from the solution. And you assume that, again, for the whole time interval t, the inputs are fixed. So what does that let us do? Well, the first thing you can do is you can pull this v out of the integral. Once you have this integral, you can then solve it. Then you actually do the integration, and you can get this, this term here. And we notice that this is just a bunch of set operations, and you end up with a set of states. And so this is my one-step fixed input effects term that I describe as just a set of states. What about if we had multiple time steps? So I'm considering now at each time step you have a fixed input, but between time steps now your inputs can change. So again, you can write the solution at time 2t in terms of the solution at time t. So the solution at time 2t is just you take the previous time solution, you evolve it for time t, and then you do a Minkowski sum with the input set that you had computed before. If you expand this out, substituting what x sub t is, you get this equation. If you multiply this in again, now you get sort of this equation, where after 2 time steps, what you need to do is you consider the input-free solution evolved for 2 time steps. That's sort of what we had before. The input set evolved for 1 time step, and then the input set not evolved more than just the original computation of the input set. So after I time steps, you end up getting this sort of Minkowski sum, this infinite Minkowski sum, or this Minkowski sum of I terms, where to get the set of states at each particular time, what you have to do is update this term and then add another input at the previous time step, basically. So that's the math part of the talk. Let's go through an example now of where this might be useful, right? So the example I'll use is a parameterized spring mass system. So you can imagine you have you have a bunch of masses that have springs connected to their neighbors, and at the end there's sort of walls. Whenever you have a mass, it has a position in this system, and it also has a velocity, right? So each mass that you think of adding to the system will add 2 variables to the system. So you can pick however many masses you want, and therefore however many dimensions you want for this problem. To make things simpler, we'll take the masses to be 1, we'll take the spring constants to be 1, so then sort of easy to represent. And then what's a specification for this type of system? So if you want a formal specification, you could define things like the first mass doesn't touch the wall. So if you have a certain width, you could imagine these things are moving. You don't want to run into the wall. That could be a specification. Maybe the two neighboring masses don't touch each other. You could define that with this mathematical equation. Or maybe there's sort of some maximum velocity for masses. Those are all valid specifications. And those are things you could check using set operations, right? You compute the reachable set of states at each point in time, and then you check if it intersects with these properties. Okay, what about the initial set of states? So say I had a system where this is the position of the zeroth mass, the velocity of the zeroth mass, similarly the position, velocity, and so on and so on. And so my initial state is everything is 0 except the velocity of the first mass. So it looks balanced, but then the first mass is moving. And so everything will sort of move back and forth. And I want to check if a particular specification, for example, the position of the first mass, is violated for a particular, for a system that has, let's say, a single mass, right? How could you check this type of property? Anyone have any ideas of a way to check this property? So I mean, this is a deterministic system, and it's a fixed initial point, right? So what engineers do is they do simulations, right? And so we know simulations aren't sort of, if you use the standard simulation algorithms like Runge-Kutta or something like that, you're not going to have a guaranteed solution. But in general, they're very accurate. And for this particular system, that would be the fastest way to probably answer this question, would be run a simulation. And you could imagine if you have 2 or 10 masses, you could do the same type of thing. So let's look at a simulation. So this is the spring mass system that I had. This is a one mass case, right? So we have a single mass. We have the springs on each side. It starts out at position 0. This is the phase space plot, right? So this is the x-axis is the position, and the y-axis is the velocity. So initially we have this initial point. We can simulate this system. And you can see that this is just plotting the position over time and the velocity over time. For a single mass, it's a pretty simple system. You might have guessed that it just sort of oscillates back and forth, right? Let's consider more masses. So what does it look like if we have 2 masses, right? So now you can see the phase space has a much more complicated behavior. And so it's not really clear if I had a property like the position is always greater than minus 0.6. Is that violated, right? Oh, looks like it was violated, right? We do a single simulation. We can check formal properties. If we start to get more and more masses, and you look at the sort of behaviors you get, they get sort of even more complicated. So now if you were looking at the system, you might think it converges to the origin, but it's actually just all the energy in the system is over here. Eventually, now the first mass is moving again too. So the behaviors are pretty complicated, is the point.
And it is a linear system, of course.
Yes, so it's a linear system with those the dynamics I had shown before, which were.
So I have a question. So here you have no inputs in
Yes.
the system.
Yep.
But I didn't know if you want to prove things. You assume that on each sampling time the input is constant. So you will lose some trajectory. So how do you manage when you
is moving? So there's the typical way it's handled is you compute the set when the inputs are fixed, and then you reason about when the inputs change, how far can they change from any of the fixed inputs, and then you'll bloat the set based on that.
But how to do this?
So there's a page of math I can show you where
Okay, but it's not so easy.
it's a page of math. So is that easy? I don't know. If you sat down with it for
It looks not so difficult because you have some kind of x dot equal ax plus belongs plus an interval. So it's difficult to integrate this.
I can show you the exact paper where they do this formula. Maybe during the break, I'll show you this.
Okay.
Yep.
That's good. Just give me the reference. Okay.
Sure. Yeah. So it's a good question. To me, I feel it's more difficult dealing with the fixed case, and then what it just becomes is you do the computation once, how much you need to bloat, and at each step you add this bloating term. So.
But this system doesn't have any input?
No. So this is a no input system. So. And it's linear. So if you look at the...
But the first push for the mass to start oscillate is considered as an input?
we consider that as the initial state of the velocity of the zeroth mass. Yep. Okay. You could imagine adding inputs where you change them over time, but for this one it's just... so if you want to analyze a system where you have fixed inputs, it's the same thing as you add a variable to your... a variable for each input to your system, you add a new variable, and you set the initial values of the, so you have an input within a set, you set the initial states to be that, let's say, interval, or that set of states, and then you set the differential equation to be the input is 0, x dot equal, or u dot equals 0, and then that'll be the case where you have fixed inputs forever, right? This was the dynamics, so it's a linear system and no inputs right now. Right? So what about uncertainty, right? So simulation is great when you don't have any uncertainty in your system. In this case, rather than considering a single initial state, what if we actually could only measure this to a certain precision? So everything's within plus or minus 0.2. And so then the question becomes, can you check if there exists any initial state that violates the specification, subject to these uncertainties? So the first representation is kind of the easiest one to understand. It's a vertex polytope. And so we want to capture, we're tracking sets of states, let's use polytopes, right? So it sounds like a good idea. The way a vertex polytope represents states is using the corners of the polytope. So you have n-dimensional state space, you have n corners, and if you took the convex hull, you would have the set of states being represented. The time elapse operation, how do you compute that? For a vertex polytope, it's pretty simple. You take every vertex, and you compute e to the a delta times that vertex. So this vertex, let's say, becomes this one becomes this one, this one becomes this one, this one becomes this one, and now you have a new vertex polytope. That's the time-evolved vertex polytope. Checking if the intersection is empty, which we need for safety verification, is also pretty simple. You just go through every vertex and check if any of them violates the property. Since these states are convex, this is sort of sufficient. If any of the corners violates the property, then there's some initial state that had violated the property. Yes?
What is a polytope?
Okay, polytope is it's a generalization of a polygon. So like in 2 dimensions, you could have triangles, squares, pentagons. You have some shape. Polytope would be a higher dimensional version of this. So.
But you said that there are n vertices when you have n dimensions.
No.
No. Okay.
You have many more vertices.
Okay.
So even in 2 dimensions, a triangle
so
will have 3.
Arbitrary many.
Yes. Even in 2 dimensions, you can have arbitrary many. Right. Okay. So a little, the complexity of this will depend on how complex your initial states are, as well. But it need not be a box, right? You could imagine you have triangle initial states. I've seen certain papers where you consider the initial states are some steady state of the control system. So then it's really some n-dimensional line segment that they were considering to be the initial states. So vertex polytopes can handle that. So then this is sort of a reachability algorithm for fixed time step reachability algorithm. Yes?
Just a follow-up question. Maybe it's not n size, but is it kind of order n, or is there a typical order?
So it depends, right? If in general, the question, you could have one that's order n, like a simplex in higher dimensions. Each time you add 1 point and you get one more dimension. For a box, that's not the case. We'll see that being a problem in the future. But you could imagine a box, if you have 1 dimension, it's an interval. There's two corners, 2 sides. 2 dimensions, it's a box. There's 4 corners. 3 dimensions, it's a cube. Now you have 8 corners. In general, and we saw the computation, it's 2 to the n corners, right? So in high dimensions, that can become a problem. But we can, for low dimensions, we could still imagine using this for reachability computation. So the algorithm would be for each multiple of your time step, you go iterate through each vertex of your initial set of states. You compute this y e to the a n times delta z, where z is your vertex, n is the step number, a is your dynamics matrix. Then you take the vertex that you computed and you check the safety formula with it, right? And if that's always safe, then you can say your system is verified within a discrete time fashion. So let's look at that approach. So this is the same system that I had before. The simulation here corresponds to this star, but actually we're considering intervals of initial states, right? So it's not just this, it's actually there's states around this that we want to consider as well. So if we use a Vertex Polytope, this is actually the set of initial states that we're considering with that plus or minus 0.2 noise. Now if we start the system, we evolve it over time, we get these sort of this nice expected behavior for at least the case where we have one mass. As before, we can consider adding more masses to this system. So let's consider 2 masses. This is the phase space plot for the first mass, remember. So this is the position of the first mass and the velocity. We're not showing the second mass at all. Initially, all the vertices are still the corners, but remember now, this is no longer a 2-dimensional system. This is now a 4-dimensional system. So the number of corners is 16. Right. And so if we run this system, we can see actually these 16 corners, how they evolve over time. And so the dotted line is really the sort of outer approximation of these 16 corners. Let's go a little further. If you were to track any one of these corners individually, you would notice that you can't really ignore any of them because the way that it works, they'll sort of rotate around, and eventually some of them will become extreme at some point too. So everything affects everything else. But still, this is sort of fairly fast. So for a 2-dimensional system, this doesn't really have many problems. If we start getting bigger, let's look at a 5-dimensional system. As you can see, there's a lot of corners now of the system that you have to track at each point in time. But computers are fast and simulation is fast. So still here at each sort of point in time, it takes about 20 milliseconds to do this update step. If you go slightly bigger, 7 dimensions, you can see it's starting to slow down a little bit now. The update time is 300 milliseconds. If we turn this off for a second and let it spread out, there's a huge number of these corners that you need to update. And so, I mean, I can tell you exponential growth is bad, but if you see it and do the computation, you can really see that beyond, this is a 14-dimensional system, like this method isn't really going to work.
I'm sorry, what do the different points represent? Are they the bounds for the positions of the different masses?
Mm-hmm. So the red dots are all corners of the initial state space. So the initial state space, each dimension has an interval that it can be.
So each dimension being the position of each mass?
The position and the velocity.
Oh, right.
Yep. And then so you can consider one combination of maximum position, maximum velocity of the first mass, maximum position, maximum velocity of the second mass. And if you flip any one of those, you'll get a different point that you need to track.
And how can I define the distance between every vertices?
What do you mean define the distance between every vertex?
Like every point is, or a vertex is like an initial state.
Mm-hmm.
So how can I define like this one? The next one is about 10 distance from it.
Mm-hmm. So initially it's easy because it's given as your initial state conditions. To do it after some amount of time, you do the time elapse operation. Mm-hmm. So you take this point, you take e to the at, and you multiply it by the point, and you'll get the time elapsed point. Mm-hmm. And you do the same thing for its neighbor, and then you have the 2 neighbors. Mm-hmm. And then this is just drawing the projection onto the first 2 dimensions, basically.
Is this the exact solution, or is it an approximation?
So where would inaccuracy come from in this case, right? So you're computing matrix exponential. That's one thing. One case where you could imagine I'm using floating point to compute matrix exponential. And you're also doing matrix vector multiplication. That's another point where I'm using floating point. In this case, it's all floating point. But there probably are algorithms to do, for example, you could do interval bounds on all of these things, and you'd have guaranteed algorithms, right? So it's not the, in this case, it's floating point, right? But it's not, that's not an algorithmic problem. You could also do it in a guaranteed way. Yes?
So if I decrease the time step at which I do the time elapsing operation, I will get less red points
So,
at the end.
yep, the number of red points is based on the number of corners of the initial states. So the time step doesn't change that. All that would do is, so this is the update time per one step. So if you if your time step is smaller, you need to do more updates to get to the same time bound. Okay. Good.
So V polytope means zonotope, or?
V polytope is a vertex polytope, the vertex representation of a polytope.
Okay. But it is a zonotope, what you're saying.
Not necessarily, because a triangle, you could represent that by its vertices, and that would be a vertex polytope.
But if you start with a box?
If you start with a box, then this is always going to be a rotated rectangle, I believe. So a box is a zonotope, yeah. So if you started with
the projection, you have the projection
Yep.
of.
Yep, yep.
Okay.
So what happens if you keep increasing the masses, right? So I measured this up to 10. I didn't go up to 45, which if you do the math, it would require more than the age of the universe, essentially. So this method will not scale to your 100-dimensional system that you wanna check. But researchers want to analyze larger systems, so they came up with clever data structures, one of which is a zonotope. Right? So what is a zonotope? It's a particular type of polytope with some restrictions. So formally, you can think of it as it has a center. It has a set of generators G, which are sort of vectors. And then for each of these generators, you look at the states with the generator plus or minus 1. So a box could be a type of zonotope where you have the center of the box, and then for each dimension, you have half of the width. And then all the points that are between the center minus half the width and the center plus half the width are part of the zonotope, right? And these generators can be in any number of dimensions. So you can represent an n-dimensional set of states with just n generators. Here's an example of a zonotope. So the way to think of this is there's 3 generators, G1, G2, and G3. If you look at the set, this is the center of the zonotope. If you just use the first generator, your set of states would be just this line segment. If you then add the second generator, you now have this dotted line. So you have this now all combinations of this vector, and then also their inverses. So you have the dotted line, and then you can add the third generator. Now you have sort of something like an octagon, right? Another way to think of zonotopes is it's a Minkowski sum of a bunch of vectors, right? That's another definition. But, what's neat about zonotopes is that time elapse for zonotopes is efficient. So the way time elapse works is, again, using linear transformations. You want to multiply every point in the set times a matrix. And you can do that with zonotopes by basically multiplying the center times the linear transformation, as well as each of the generators, essentially, too. So if you have an n-dimensional set of states with n generators, now you only need to do n matrix multiplications plus 1 for the center. And you have a new zonotope that represents now the time elapsed set of states. What about checking for intersections? So zonotopes, you can also do checking with intersections against linear constraints. And so the way to see that is sort of easier with an example. You could imagine you were given a zonotope with this center and 3 generators, and you wanted to know if there's any point in the set where this condition is violated. So the idea is you would start at the center, and then for each generator, you maximize this linear constraint, and then see if the number this comes from this constraint, right? and then you see if whatever you ended up with is greater than 12. So from 0.23, you could take the first generator, you get to 3,3. You can always go either in the positive or negative direction, right? So that's what you choose which direction you should go to. Eventually, after you get through all the generators, you go to this 0.45. You plug in 4,5 into the linear condition, and you get 13. 13 is greater than 12. So therefore, this condition is violated in that zonotope. And so this is exactly what we need for safety checking, right? We check linear conditions against the set of states. So let's look at a demo. So let's see. Again, we have the spring mass system. I'm just going to show the Vertex Polytope for easy explanation. When I do zonotope, it adds the generators onto the plot, right? So for every dimension, there's a generator. So initially, the sort of red generator is here, and the blue generator is here. If I want to maximize, I can click, and hopefully it'll go from the center to along each of the generators to a point that maximizes the constraint, in this case in maximum x direction, so maximum to the right. And you can see if I evolve the set of states, the generators evolve as well, but they stay, stay within that set of states, and that maximum, maximizing in the x direction, you notice doesn't in fact maximize within the set of states. Let's see, 2 dimensions. So now it's a 4-dimensional system. There's 4 generators. I can think of doing the same thing. The generators themselves are sort of vectors, right? But when you start putting them together end to end, you can, again, maximize in particular directions, which is what we need for safety checking. Let's go a little bit higher. So now you can see really it makes use of all the generators as it's going. You can get to some sort of maximum set of states. This is going slow because I'm still using Vertex Polytope. If I turn off Vertex Polytope, now the update time is much lower. And now I can go significantly higher. And still the update time stays very small. The number of generators increases sort of linearly with the number of dimensions.
Why is it linear?
So each generator, the way you define a set of states is it's the center plus the number of generators. And so if you wanted to define, let's say, a cube, right, you would have one dimension for the x variable, one generator for the y variable, and one generator for the z variable. Yep. So this is neat, right? If I wanted to know what's the minimum x that can be achieved, I can then just minimize over the generators, get this point, and then check if I violated my safety condition. So zonotopes are neat, and they scale to higher dimensions, but there's still some drawbacks of zonotopes. So one of the things you may have noticed is the way these generators are zonotopes are defined. They're always centrally symmetric because you always have this property of generator plus or minus 1. And not all initial sets of states are like that. And then especially when you look at discrete transitions, after taking an intersection, even initially if you started with a nice box, the set of states that takes an intersection won't be a nice box. It'll be a more complicated set. And so if your representation is a zonotope and you want to be conservative, you end up having to over-approximate things. And that causes error in the analysis, which you want to avoid. There's other things that you can't do exactly, things like union or intersection. So if you read the research papers on this, they'll describe ways to over-approximate this, right? So the next sort of data structure I'll talk about is support functions. So a support function is another representation for a set of states. The way it works is it maps. You can use it to represent any convex set, so it doesn't have to be centrally symmetric. It maps each vector to a distance, a signed distance from the origin projected onto direction d. So if this is the origin, you can imagine this is my direction d. how far can I move in this line and reach the outside of the set. This will be the value of the support function for this direction. And you can imagine if you do this over all directions, you'll sort of sweep the outside of the set, and then you've defined the set of states that way. So it's a little bit more general than zonotopes, right? It doesn't need to be centrally symmetric. You can do approximations of complex sets using zonotopes. So if I have a very complicated set of states I'm tracking, I can imagine computing the box over approximation of the set of states. That's just, you take a support function and you evaluate it for particular directions. So the real support function might be sort of this very complicated thing, but I can sample it in certain directions very quickly. So this would be shown here as this is a set of states I'm tracking, and then I have 4 directions that I care about, and then I maximize in those 4 directions, and I get 4 lines, and then I measure those from the origin to get the value of the support function. So you can use support functions to encode reachable sets. So this one, they didn't just encode a set of states at particular points in time, they actually encoded sets of states up to a certain time. So this is the box representation. So you have some real set of states you're tracking. And now this box, omega 1, contains all states reachable between time 0 and time delta. If I use different support function directions, I can get a sort of more accuracy, right? In this case, I use, I think, 8 different directions. And now it's you get this 8-sided shape that encloses the set of states. And you can increase this to as much accuracy as you would like. This allows you to basically trade off computation time and the accuracy of your analysis. Because if you have more directions, you'll get a sort of a better approximation of the set of states. As opposed to if you have less directions, then maybe it's faster because you don't need to evaluate as many directions. The other neat thing is for support functions, linear map is efficient. So if you want the support function after you multiplying by some matrix A, you can just modify the directions that you were considering and evaluate on the initial set of states. So that's what we need for time elapse is linear map. Another thing is Minkowski sum is efficient. Right? So Minkowski sum consists of just adding support functions together. So if we have 3 sets, I believe, here, so I have the set C, the set Q, and the set P. I can just look at, if I wanted to do a Minkowski sum, I can just, if I want to evaluate the support function director of the Minkowski sum of the support function direction of the Minkowski sum of these states, I can just evaluate them individually and add them together. So for example, what's the maximum y for this set of states for this sort of Minkowski sum of 3 states? Well, I can do what's the maximum y for Q, maximum y for P, maximum y for C, add them together. Now that's the support function value for the Minkowski sum, this sort of outer box that we've considered. Checking for intersection is nice because it becomes linear programming, which is efficient in high dimensions. It basically consists of evaluating the support functions in certain directions.
Sorry, but L shouldn't be a vector of norm 1, because if it's a direction.
You can define it both ways, probably. Norm 1 would make sense. Otherwise, there's some redundant information, right? Yep. There's also, okay. Yeah, so either one is okay. So let's look at doing this spring mass system now with support functions. Mm-hmm. So again, we have the, let's start with 2 dimensions. If we add support functions, what this will do is actually it's the red dotted set of states around here. So initially it's just a box, and I'm evaluating box directions, so only 4 directions for the support function. So you can see that even though the set of states is actually pretty complicated, by looking at support functions, it lets me get sort of the minimum and maximum in each of the directions. And this is true also as you go to higher dimensions. You can get the box over approximation. And if I turn off the Vertex Polytope. I should be able to go to higher dimensions, and my update time stays very small, right? If I wanted a more accurate set of states, as I mentioned, you can trade off more computation time by adding more support function directions. And as you add more and more, you'll get the sort of real set of states. So you can see now the set of states is actually very big. That's reachable. So support functions, they allow you to efficiently compute linear maps, but there's still some drawbacks in that you still need to compute the matrix exponential. So in high dimensions, that can still take a lot of time. There's other limitations. The initial states must be convex because support functions represent convex states. And then intersections become a little bit more tricky. If you want to actually take an intersection of a support function against a guard set, typically they don't do it directly. Instead, they'll do things like template polyhedra, where you take your set of states, you over-approximate it by, let's say, the box, right? I have this complicated set of states. I can't do an intersection with that. So I can compute the outer box, though, and I can do an intersection with the outer box, and then I can proceed forward. So this causes some error, right? But it lets you keep doing the computation. So I think the last data structure that I'd want to cover is a generalized star set. But I'll save that for next time, I think, and sort of stop here for now. Thank you.
Any questions?
The simulation which tool? It's Python?
Yeah, so I'll try to make the code available probably so you guys can use it. It's Python code. And it's not even a big file, so it's one file. Like the simulation is not too bad. It's using matplotlib for plotting, so drawing a box is not too bad. The overhead, most of the computation is what dominates the overhead. So.
Yeah, another question.
Yes.
Here you have infinitely many directions, but then you decide infinitely many L, but then you
Yes.
decide to use only some of them.
Yes.
Do you have to commit at the beginning how many direction you use, or you could decide to increase them or decrease them during simulation?
So there's nothing stopping you from increasing or decreasing them during the simulation. It's sort of a research question, right? What would be a good strategy to take for increasing or decreasing them? So the easiest thing you can do, and what SpaceX, which uses support function supports, is you can give fixed directions, right? You can do box, you can do uniform directions, you can give it specific directions you care about. So the guards are usually good directions to use. But I think there's been papers about doing something more dynamic, right? And so the question would be, what's a good strategy, evaluate it, and publish it, right?
Other questions?
No, my question was about the support function, but you just
Yep.
answered that.
Okay.
That's fine. Thank you.
Other questions? I have a somewhat technical question.
Sure.
Are the libraries doing directed rounding?
Are the what? Sorry?
Are the libraries doing directed rounding? So
What is directed grounding in this context?
Directed rounding is when you work with intervals, you round up.
Oh, directed
Yes.
rounding, I see.
Yeah.
No, not these ones. So it's actually an interesting question about what's the best way to, we have a finite research effort, and we want to do research on this area, right? So ideally, you would have a tool that's sort of formally verified itself. It uses directed rounding whenever you do computations. When you do linear programming, maybe you use exact ones as well. So if you do that, you can be successful on it. And there are certainly efforts where people do that. It'll slow it down a little bit, obviously, too, because there's sort of overhead in doing each of these things. It'll slow down the computation. It also slows down development time. So in this case, I want to see how well can the algorithm itself scale without any of the sort of overhead from these sort of more verified methods, right? So in this case, I'm just using floating point computation. So one thing I would say, though, is the purpose of verification is to increase your confidence that the system is correct, right? So Remember the F-16 ground collision avoidance? They didn't use any formal methods, but they trust the system's correct because they did a lot of simulation, right? So if you ran this type of analysis and let's say it finds nice counterexamples for you, that's very useful anyway. And if it says there are no counterexamples despite all the floating point computation, maybe you wouldn't bet your life that there are no counterexamples, but it certainly, I think, increases your confidence that the system's correct. So that's the more philosophical angle, I think.
Is the simulation work for each initial state individually? Like it work for the initial one and then the second one, commute it individually, or predicts the second initial state from the first one?
So what do you mean by second initial state?
Not second initial state, like we have a different set of initial state. So the first one, it commuted it, and then the second one, it commuted, or we can compute the second one just by prediction from the first one.
So in this case, they treated them, in the Vertex Polytope case, you
Yeah.
mean? Yeah, so that one they were treated independently. I didn't recompute matrix exponential because that's something you compute once and you multiply each of the corners by the matrix exponential. So for each step I did that once, and then I did a matrix vector multiplication to get the time evolved set of states. Okay, thank you.